I'm Adrian Cho. I'm a staff writer at Science Magazine. My guest is Umesh Vazirani, a computer scientist at the University of California, Berkeley, and we're going to talk about quantum supremacy. Umesh, just to make sure that we're all on the same page here, let's define what quantum supremacy is. My naive understanding of this is that it means that you've demonstrated that a quantum computer has done something that's just beyond the capabilities of a conventional computer. Is that the right understanding? What exactly is it?
Yeah, so I think, quantum supremacy goes back to this notion that quantum computers are exponentially more powerful than classical computers. And, um, this notion goes back to the birth of the field. So, back in the 90s, at a theoretical level, when we were studying the foundations of computer science, we actually demonstrated uh, that there were theoretical problems that quantum computers could solve exponentially faster than classical computers. And and so this was a really interesting thing from the point of view of what computers could do. Now, the early demonstrations of this theoretically were with problems that were completely useless. They were just benchmarks that quantum computers could solve much faster than classical computers. And then later there were useful algorithms like Shor's algorithm for factoring integers. So quantum supremacy is the experimental recapitulation of that development. So it's showing that there's some problem that you can solve exponentially faster on a classical computer than you can, or on a quantum computer than you can on a classical computer.
Right, and in fact, this has been attempted, right, or has been demonstrated. In 2019, researchers at Google used a 53 quantum bit quantum computer, 5253, to solve a particular problem that they say would overwhelm the best supercomputer. So, in a sense, quantum supremacy has at least been claimed once. So, why is that not game over? Why is there a further question now that Google has done this demonstration?
Okay, so Adrian, that's a really great question. So let me try to unpack that a little bit. Okay, so there are two aspects to quantum supremacy. One is it's a milestone on the path to a viable, practical quantum computer. And the second thing is it's a fundamental physics experiment that tests quantum mechanics or physics in the limit of exponential complexity. And so what Google did was it was a great step forward in terms of hardware or experimental capability. But together with that, there was a theoretical justification saying that plausibly quantum supremacy had been achieved in the sense of testing quantum mechanics in this regime. Now, and plausibly as a step as a milestone towards a practical quantum computer. Now, there are two caveats. There's a caveat on each of these. In terms of the achieving, a test for quantum mechanics in this regime, there was a plausibility argument, but this is an important experiment, and it's not a one and done experiment. So it's something that's going to have to be refined over time to make it more and more plausible that it's been achieved. So the theoretical evidence for supremacy in this case, it was plausible, but it's not yet overwhelming. So that's the one thing. The second aspect, which is as a milestone on the way to a practical quantum computer. So there was one aspect of this experiment which is very interesting, which one would like to overcome, which is that in order to actually interpret the data, so the quantum computer outputs something, and now this something, in order to understand it, you have to use an amount of of classical computation. So you have to use a supercomputer to interpret the results. And the amount of computation that the supercomputer performs is larger than the amount of computation it would have taken to solve the original problem on a classical computer. So in that sense, as a milestone on the way to a practical quantum computer, it also leaves something to be desired. And so the next step in this whole process would be an experiment which achieves quantum supremacy, but now does so in a way that's where the plausibility argument is more compelling than this first one, and also in a way where you do not have to work so hard to interpret the results, the output of the quantum computer, where you can take the quantum computer's output and use a small amount of computation on your classical computer and actually understand what the output was.
Okay, so just to make this a little more concrete for the viewer, what Google did essentially was they had this quantum computer, and they essentially had it do a fixed but random set of logical manipulations, logical gates, if you will. And since it was 52 qubits, there are, if you interpret it digitally, the possibility of 10 to the 52 different outcomes. And this random set of random gates should make some outcomes more likely than others and give you this kind of pattern. But the issue was that you had to show that you were getting the right pattern, right? That, my understanding, if they were just noisy classical bits, then all outcomes should have been, roughly speaking, equally probable. Some are more probable than others if it's doing something quantum. But to really know that that's what's going on and it's not just some artifact or something like that, you have to show you get the right pattern. And that's where the classical computation came in, right? So they would start with a smaller number than 52 qubits. They would work their way up trying to find this random pattern produced by the random selection of logical operations. And at some point, they couldn't keep up, right? The classical computer couldn't simulate the output of the quantum computer, and that's when they claimed supremacy. But in a sense, what they were doing was producing this very complicated quantum state, and to demonstrate that it was actually doing what they wanted it to do, they had to try to then simulate it with a classical computer, correct?
Yeah, so that's right. So the way to look at it is that the output of the quantum computer was a particular probability distribution on those 52-bit strings, and you could get the same kind of distribution using a classical computer, but which particular 52-bit strings had higher probability than average and which had lower probability than average would be different. And the particular pattern that this random quantum circuit would produce, there were reasons to believe, this is where the plausibility argument comes in, that it's hard to do. It's exponentially hard to do that classically. But exactly which pattern the quantum computer is producing, you have to verify that. And to verify that, it actually takes you an amount of computation to know which ones are going to be more likely, which ones less likely. That's a really hard problem. And so you use the fact that 52 is not yet so large that you can't do the simulation on a classical computer with some additional assumptions.
Right. So what you're talking about are new methods to demonstrate quantum supremacy without having to do such a massive amount of classical computation to verify the quantumness of the system. So let me ask, generally, how does this work? There must be some element you're adding in.
Yeah. So let me just say that eventually, when we actually have a practical quantum computer, what we'd like to do is have the quantum computer perform a computation and then use a little bit of time, take the output and use a little bit of time on a classical computer to say, here's my final output, right? So we don't want to actually, if you have a 500 qubit quantum computer, we don't want to then take exponential time in 500 on a classical computer to interpret the output of the quantum computer. So in that same sense, while we are doing supremacy experiments, the next challenge is, can we look at the output of the quantum computer and in using a relatively small amount of time on a classical computer, actually verify that it actually achieved quantum supremacy.
Right. So this would be, for example, if if you could run Shor's algorithm right now, if you had a quantum computer that was good enough to do that, and you gave it some gigantic, 1,000 digit number, and it factored it, then the fact that multiplying the factors is relatively easy to do, you could check that very quickly. You could just take the two factors that the quantum computer had given you, multiply them together, and see if it gave you back the original number that you gave the quantum computer. So that's an example of using just a little bit of classical computation to prove that the quantum computer did what it was supposed to do, correct?
That's right, and that's where we would hope to be eventually. But
Right.
you know, um, the the point is that particular application we'll get to after we already have practical quantum computers. So what we'd like to do is find some other way of uh, of proving the quantumness of this quantum computer, um, well before we end up with a useful quantum computer. So
Right.
we want it to be a milestone on the path towards achieving a useful quantum computer.
So what is your approach? How do you do this?
Okay, so the idea is actually quite simple. So what we do is um, we um, we appeal to cryptography. So in cryptography we have um, um, we have functions that are easy to compute. They're hard to invert. So they take exponential time to invert unless you know some secret information called a trapdoor. And if you know the trapdoor information, you can actually invert this one-way function quickly. And so now one of the things that you can do is, since quantum computers can solve certain problems exponentially faster than classical computers, but they're not all powerful. There are certain problems where we believe that they don't give you much speed up or any speed up over classical computers. And so there's a whole branch of cryptography based on this, which is called post-quantum cryptography, where it's cryptography that you can implement classically, but where even a quantum computer cannot break it. And so our idea is to use this kind of cryptography to to sort of level the playing field between the classical verifier of this quantum computer and the quantum computer itself. And so, by interspersing in there a task, namely, this crypto system, where the classical experimentalist or verifier has the trapdoor information, and so can do something that even the quantum computer cannot do.
But just to make sure, there's a subtlety here, right? You are not, for instance, simply saying that the quantum computer has to break post quantum cryptography, right? Because post quantum cryptography is supposedly unbreakable. So it's a little more subtle than that, right? You're looking for a problem that uh, that the quantum computer will still have an advantage over the classical computer, but that if you're the poser of the question and you have the trap door, it gives you an easy way to check. Is that correct?
Yeah, so it's a little bit of, so the wrong way to use this post-quantum cryptography is to sort of hobble the quantum computer. So that would not be a nice way to interact with the quantum computer. Instead, what you want to do is you want to allow the quantum computer to do its uniquely quantum things, to make its uniquely quantum computations, while making sure that it's playing somewhat on the turf of this classical verifier who has a trapdoor information. So it's to tie the hands of the quantum computer just a little bit, but not so much as to hobble it.
Mm-hmm.
And this requires, this is what takes a bit of doing. And so you have to think quite a bit about how to adapt the cryptography to make it possible for the quantum computer to compute despite having its hands tied behind its back a little bit.
But just to make sure I've got this clear, I mean, this is not simply speaking in generalities, right? You and your colleagues have identified, at least one specific sort of family of functions that could be used in this type of a test. Is that correct?
Yeah, so that's right. So we did identify a family of such cryptographic functions which had this property, and this was this is work that we did at Berkeley with some of my students, some of whom are now my former students, as well as uh, a colleague who is visiting us in Berkeley. So yeah. More recently, I've been collaborating with some colleagues in physics in our physics department to actually greatly expand the kinds of crypto systems that can be used in such a protocol. And so the new protocol is almost as simple as the previous one, but it's something that allows us to, it uses some more uniquely quantum features to allow a much larger range of cryptographic functions to be used. And so as a result, that makes it potentially much more scalable and practical. So we are, that's what we are actually exploring right now.
So, let me, if I might, just ask this question. One of the criticisms of the Google result was some people argued that essentially what Google had done was to create a very complex quantum state that was merely very hard to simulate on a classical computer, and that sort of detached it from any sort of real practical use. Obviously, once you start bringing in elements of cryptography, you're getting closer to things that may be practical. So, does this approach of yours will it give you insight into what the quantum computer might actually be doing that's useful? Will it be closer to some sort of useful task?
You know, I would put it somewhat differently. I would say that what Google did was a real step forward in terms of saying, here's a benchmark that our device can meet. That we don't think any classical device could have met, and that's a valuable thing to do. And now what we are suggesting is there's a way to move forward and create another benchmark, but this benchmark has the virtue that in order to verify that the benchmark has been achieved, you don't have to work so hard. So you don't have to work exponentially hard classically. And so, that's important because eventually we do need to, that's a much more realistic benchmark in the sense that eventually we want to solve problems on a quantum computer that we don't have to work exponentially hard then to decipher what the quantum computer actually told us. Right.
So
So
let me ask,
that's
so I'm wondering, have you spoken with experimentalists? Will people try to implement this?
Yeah, so we have spoken to experimentalists, and in fact, there's a there's a there's a proof of concept experiment that's going to be carried out at IonQ on this, and that'll probably give us some insight into what it'll take to scale it up to the point where it's totally convincing by itself. So that'll give us some insights. We're also talking to others about it, and we are trying to see how to make this experiment really fit into uh, various machines at this point.
Okay, great. Thank you, Umesh, for taking the time to discuss this. It's an exciting topic. It's interesting to know that quantum supremacy is not simply, a milestone that's passed, but actually is an area that's going to continue to be interesting. Thanks so much for taking the time to discuss this with us. I'm Adrian Cho for Science Magazine. Thank you.
Thanks, Adrian. It's a real pleasure.